Welcome to this class. In this class, we are going to introduce the concept of limits. So we start by giving the informal definition of a limit, and then give the formal definition of the limit, and then see how we can evaluate limits using numerical method. And then later on, we'll state laws of properties of limits, which we'll use in the next session to evaluate limits of some elementary functions. So welcome, class. So we are introducing limits. So first, let's start by giving the informal definition of the concept of a limit of a function. So a limit of a function f of x or we can say a function f of x has a limit L as x approaches or we can say tends to value A if the value of the function can be made as close as we like to L by taking x sufficiently close to A. But we don't have to be at HTL, but not equal to A. So this way, how we define limit of a function f of x informally, that a function f of x will have a limit L as x approaches or tends to a value A if the value of the function f of x can be made as close as we like to L by taking x sufficiently close to A. And then this x need not be necessarily exactly equals to the value A itself. So we use the notation lim x then this means limit of f of x as x tends to a is L. So this is how we read this statement, that limit of the function f of x as x tends to a, or we can say as x approaches a, is equal to L. So then now let's give the formal definition of the term limit, which we can use to prove limits of functions. So formal definition. Of a limit. Now, formal definition of a limit is given using epsilon delta values. And the statement goes by, we say that a function f of x approaches the limit L as x approaches a and this we write lim f of x approaches a equals to L if for every positive number epsilon there exists another positive number delta possibly depending on epsilon, such that if the absolute value of x minus a is less than delta, then absolute of f of x minus L is less than epsilon. Or we can say whenever we can say that the absolute value of f of x minus L is less than delta whenever absolute value of x minus A is less than delta. So it should be very clear that the formal definition of a limit does not tell us how to find the limit of a function f of x but enables us to verify a suspected limit is correct. So that should be very clear that whenever you are using epsilon delta in any definition of a limit is only to help you to show that the given limit is correct, but does not evaluate the limit of a function. So the key thing is that we're saying that we use the formal definition of a limit to prove existence of limits, or simply to prove limits. And let's see these few examples. So let's call them appetizers. One, verify that limit of the function 3x plus 1 as x approaches 2 is equals to 7. And this is how you provide the proof. So proof, you start by giving the definition of a limit formally. And this is how the stem of the proof is. So you say, let epsilon greater than 0 be given. So the goal is we find a delta which is positive such that absolute of f of x minus L is less than epsilon whenever absolute of x minus A is less than delta. And in our case, A is 2, f of x is given by 3x plus 1, and then L is 7. So then this means that absolute of f of x minus L, in this case, is 3x plus 1 minus 7, which is the same thing as saying absolute of 3x, 1 minus 7 is minus 6. And then we expect this to be less than epsilon from the definition. So which implies that 3x minus 6x, you can factor out 3. So 3 into x minus 2 is less than epsilon. And we know that if I have product of two real numbers, is the same as absolute value of product of two real numbers is the same as product of their absolute values. So this is the same as absolute value of 3, absolute value of x minus 2 is less than epsilon. So which implies that absolute value of 3 is just 3. Absolute of x minus 2 is less than epsilon. So this implies that absolute value of x minus 2 is less than, by dividing through by 3. I remember the definition goes that if this is the case, then absolute of x minus a should be less than delta. And remember, this is the result obtained from the absolute value of f of x minus L. So this thing, absolute of x minus 2 is less than epsilon over 3 whenever absolute value of x minus 2 is less than delta from the definition. So this means that if we choose delta to be less than or equals to epsilon over 3, or this is the same thing as just saying that you choose delta to be epsilon over 3, then we are done. Or it's as good as saying that if we pick delta to be the same as epsilon over 3, then the given limit is proven to be a true limit. So example 2. So prove that limit as x approaches 2 of x squared is 4. As usual, let, so proof, let epsilon greater than 0 be given. So we find a delta, which is also positive, so that, or such that absolute value of f of x minus L is less than epsilon whenever absolute value of x minus a is less than delta. And in our case, f of x is given by x squared, a is given by 2, and then L is given by 4. So f of x minus L absolute will be given by absolute of x squared minus 4. We expect this to be less than epsilon. And then we know that x squared minus 4 is a difference of two squares, so we can write it as x minus 2 or x plus 2 times x minus 2 is less than epsilon. So this means that absolute of x plus 2 times absolute of x minus 2 is less than epsilon. Or you can say x minus 2 absolute is less than epsilon over absolute of x plus 2. But unlike in the previous case whereby we had to divide through by a constant, in this case, we see that we are dividing through by an expression which involves the variable x. So the way we are going to interpret it is going to be a little bit different from the way we are interpreting division by 3 in this previous example. And this is how we interpret it. So we say we need the expression epsilon over absolute of x plus 2 to be very, very small. And so for us to make this one to be a very, very small x value, then we will control it by using the absolute value of x minus 2. And so this is achieved by controlling the factor x plus 2 absolute, so that it makes the fraction small. So we assume that delta is less than or equals to 1. And there's nothing special with the number 1, but we're just picking it for convenience to make our computations much easier. Another small positive number could still be related to the delta. So then now, if this is the case, then from the second part of the definition, remember we say, if we have this, this will always be the case. So which means that by taking delta to be less than or equals to 1, then we are allowing x minus 2 to be less than or equals to this number 1. And we know that if we have absolute value of x being less than or equals to a constant k, then this means that x lies between minus k and k. So this means the quantity x minus 2 lies between -1 and 1. And when I add 2 on each side of this inequality, I'll have -1 plus 2 is less than or equals to x is less than or equals to 1 plus 2. So I'll have 1 is less than or equals to x less than or equals to 3. So which means that x value lies between 1 and 3. And for me to make this fraction epsilon over absolute of x plus 2 to be very small value, then it means I have to make the denominator absolute of x plus 2 to be a large positive value, or simply a large value. So this means that x plus 2 will be large, which means then the fraction will be small. If x is taken to be 3, remember x lies between 1 and 3, so for us to have that value to be a great positive value, then we pick the maximum, i.e. absolute of x plus 2 will be absolute of 3 plus 2, which is absolute of 5, which is just 5. So if I have called this one 1, and I call this one 2, then we can say, then 1 becomes absolute of x minus 2 is less than epsilon over 5. So I can call this one inequality or expression number 3. So therefore, 3 and 2 both relates the values of the absolute of x minus 2. And remember, this was from f of x minus L, whenever x minus 2 is less than delta as given in the definition. So then this means if we choose delta to be a minimum of these two values, one which we assumed that gave us the bounds on the expression x plus 2, which was delta equals to 1, and this expression now we are getting after replacing the value of x that gives the bounds of the fraction in 1, then we are done. Or in simple terms, if we pick the smallest value, either 1 or epsilon over 5 for delta, then we will have proven that indeed the given limit is a true statement. To appreciate what we have done, let's also give another example, example 3. Prove that limit of x squared as x approaches 3 is equals to 9. So we'll follow the footstep of example 2. And so we say, let epsilon greater than 0 be given. So we find a delta which is also positive, such that absolute of f of x minus L is less than delta, less than epsilon, whenever absolute of x minus A is less than delta. And in our case, A is 3, f of x is x squared, and L is 9. So then now f of x minus L absolute is going to be x squared minus 9, which is less than epsilon whenever x minus 2 is less than delta. And then this is the same as x plus 3 times x minus 3 less than epsilon whenever absolute of x minus 2 is less than delta. That's by definition. And then this is the same as absolute of x plus 3 times absolute of x minus 3 is less than epsilon whenever absolute of x, remember this is 3, this is 3. X minus A, which is 3, is less than delta. And then this means x minus 3 is less than epsilon over absolute of x plus 3 whenever x minus 3 is less than delta. Now, at this point, you see we are dividing by absolute of x plus 3. So we are going to make an assumption on delta to help us find the number absolute of x plus 3. So we assume that delta is less than or equals to 1. So which means from this one now, we have x minus 3. So because I'm fixing delta to be 1, I can say it's less than 1. Which is the same thing as saying x minus 3 lies between 1 and minus 1. Remember, there's nothing special even if you still use this inequality sign. All of them are right. So adding 3 on each side, we'll have minus 3, minus 1 plus 3 is less than x, less than second, less than or equals to 1 plus 3, which means 2 is less than or equals to x, less than or equals to 4. So then remember, we need this positive number to be as small as possible. So for this fraction to be small as possible, then we pick maximum value of x to make the denominator larger value, so that when we divide epsilon by that larger value, the fraction is a small number. So taking x equals to 4 implies that absolute of x plus 3 will be absolute of 4 plus 3, which is absolute of 7, which is actually 7. So therefore, we'll say, if I call this one equation statement number 1, this line, then from 1, we have absolute of x minus 3 is less than epsilon, and then denominator will be 7 whenever absolute of x minus 3 is less than delta. I'm just duplicating this statement. The only difference is that now I'm rewriting this denominator using number 7, which was obtained from this computation. So therefore, the minimum value of delta will be this value that will be given by either epsilon over 7 or what we have assumed to be 1, but smallest of the two, because the interest is to get the smallest possible positive number. So if we choose delta equals to the minimum of these two numbers, the one that we have assumed and what we have gotten here are the direct relationship between this general expression that was obtained from the absolute of f of x minus L and this expression that is already given the definition of x minus a absolute less than delta. Then we are done. So that's how we prove that. And then lastly, let's give another example on this. Example 4. Prove that limit as x approaches 4 of minus 2x plus 5 or plus 5, let's say plus 15 is given by 7. So proof. So as usual, we start by giving the definition of limit. And so we'll say let epsilon greater than 0 be given. So we find a delta which is also positive, such that absolute of f of x minus L is less than epsilon whenever absolute of x minus a is less than delta. That's by definition. So here, f of x is given by minus 2x plus 15, and a is given by 4, L is given by 7. So when we say absolute of f of x minus L, we mean absolute of minus 2x plus 15 minus 7 should be less than epsilon whenever x minus 4 is less than delta. That's by definition. So we'll have minus 2x, 15 minus 7 is plus 8 is less than epsilon whenever absolute of x minus 4 is less than delta. This still means now common between minus 2x and 8 is minus 2 into x minus 4 is less than epsilon whenever absolute of x minus 4 is less than delta. This means now we'll have absolute of -2 times absolute of x minus 4 is less than epsilon whenever absolute of x minus 4 is less than delta. So absolute of -2 is +2. So which means x minus 4 is less than epsilon over 2. Now, the meaning of the value of absolute of -2 whenever absolute of x minus 4 is less than delta. So if we choose, so you can say that this and this takes the same form if we have the same expressions on the left-hand side of the inequality, so which means that we can relate the right-hand side of this side and this other side. So therefore, if we pick or take, or we can say choose delta equals to epsilon over 2, then or is as good as saying that the given limit is true statement. And then a last example on this is that you may be given a limit and then you're asked to find either delta or epsilon that satisfies the given expression. For instance, given that limit as x approaches 3 of 4x minus 5 equals to 7, find a delta such that epsilon is equals to 0.01. So what this problem wants you to do is to go through the proofs as we have done in the previous examples, and then find the relationship between delta and epsilon. And so once you have the formula relating epsilon and delta, you replace where there's epsilon by 0.01 and solve for delta. So a quick solution for this will be, let epsilon greater than 0 be given. So we find a delta, which is also positive, such that when we take absolute value of f of x minus L being less than epsilon, then that must always be true whenever the absolute value of x minus A is less than delta. And then here, f of x is 4x minus 5, L is 7, and A is 3. So we are going to have absolute of f of x minus L would be absolute of 4x minus 5 minus 7, which is absolute of 4x minus 12 is less than epsilon whenever x minus our A is 3 is less than delta. That is just by definition of a limit. So the same will mean, so common here is 3, common for 4x and minus 12 is 4. So we'll have absolute of 4 into x minus 3 is less than epsilon whenever absolute of x minus 3 is less than delta. And then you get absolute value of 4 multiplied by absolute value of x minus 3 is less than epsilon whenever absolute of x minus 3 is less than delta. Absolute value of 4 is 4, so I can say this simply means absolute of x minus 3 is less than epsilon. Absolute value of 4 is 4 whenever absolute of x minus 3 is less than delta. And then it should be obvious from these two relations. You see from this and from this one here, we clearly see that delta is the same as epsilon over 4. That's how now the two quantities epsilon and delta are related. And then given that now epsilon is given as 0.01, so this means that when epsilon is 0.01, then delta will be 0.01 divided by 4. So 0.01 divided by 4, you get 0.0025. So for this particular problem, when epsilon is 0.01, delta must be 0.0025. So that is, in a nutshell, how we prove limits. And then in the process of proving limits, you may be given either epsilon or delta, and then you're asked to find any the other known value, which is done by first going through the normal proof and see the relationship between the epsilon and delta. And then from the relationship, then you will be able now to replace the value you have in the problem and solve for the unknown. And remember that epsilon delta definition of a limit is used just to prove that given limits are correct, but is not used for evaluating limits. So in the next session, we'll be discussing different methods of evaluating limits when we have some given arbitrary functions f of x. Thank you.